Okay, so let's get started building a baseline regression model for our Hacker News problem. So in the terminal, you can see over here, I have switched over to the baseline regression model branch. Let's head over to our IDE to see what this looks like. So in this branch, in the models.py file, we've defined a baseline model class. So the baseline model class is a wrapper, basically for the scikit-learn dummy regressor class. The reason we're going to use this wrapper for building our baseline model is so that we can keep the common interface for the model in our training script, and we don't have to change our interface should we change the underlying model inside the baseline model class. So if I wanted to replace my baseline model with, let's say, a random forest, I could keep all the interfaces the same, like fit, predict, load, and save, without having to worry about what this actual model is. Like if I wanted to use LightGBM, there are like different methods to actually fit the LightGBM model. By wrapping it in this baseline model class, you can hide those details away from the training script. So now that we have some idea of what this baseline model class is doing, let's head over to our metrics.py file. So in metrics.py, sort of a similar idea to what we're doing in the models.py file. We want to create generic interfaces for all the operations we want to run in our training script. So here, instead of individually importing these error metrics into our train.py file, we're going to define this compute metrics function, which takes in a prediction vector and a target vector, and then computes the metrics for us and returns a dictionary with the keys being the individual metric names and the values being the value of these metrics. So the metrics we're going to be using for our regression model to sort of evaluate its performance are root mean squared error. This is just a nice convenient metric because the units of the error are the same as the units of the target we're trying to predict. It just makes it a little more interpretable. We'll be using mean absolute percentage error, which is also called MAPE. It's a measure of the relative error in predicting the target, just an alternative way of thinking about the error. And then finally, we have the explained variance score, which is a way of explaining how much of the target variance is captured by your model. So let's go to the train.py file. Let's see how we're using all these functions and models. In your train.py file, we basically import Comet for all our tracking, import the baseline model, import our compute metrics function, and then from data, we talked about this before in the profiling dataset script, we have our load data function and our fetch dataset artifact function. Arguments to the script are the artifact that we want to fit our baseline to, which in this case will be the Hacker News dataset. We also have a target name argument. This is basically used to just remove the target from the data frame when it gets loaded in, just so that we're passing in just the target on its own to the dummy regressor, because the dummy regressor model that we are using will not make use of any of the features. It is just fitting the strategy that is using completely on based on the target value and not any of the input features. The strategy parameter here is the fitting strategy that we're using for our dummy regressor model. For those of you that don't know, the dummy regressor model basically predict a single value for every data point in your data set based on your target, based on this and based on the strategy that you provide. So if it comes with a number of strategies, it can either predict the mean value of your target, it can predict a percentile or quantile value for the target, or you can predict a constant user-defined value for the target. So we're just going to use mean and quantile as our strategies. And if we were to pass in a quantile strategy for the dummy regressor, we would we'd have to provide the quantile that we want the dummy regressor to compute. And so that's what we would do with this argument here. And then finally, based on our experiment requirements, all scripts that produce experiments are required to have a message parameter. And so that's what this is. So going to the main function, basically we initialize the experiment, fetch the dataset artifact, which returns this configuration dictionary, and then we load in the training data frame, the validation data, drop NaN values in the target so that we don't fit anything. I'm pretty sure like the dummy regressor will throw an error if there are NaN values in the target, and then we define our baseline model with these parameters that we passed in, so the strategy, and if we were to use a quantile strategy, what that value of the quantile is that we want to compute, and then fit the model. And next, what we're doing is, I don't know if anyone noticed, but like in the compute metrics function, we didn't really define or provide any way to append some sort of prefix or indicator for whether or not this metric was computed on the training data set or the validation data set. So what we're doing in the train.py file is we're using Comet's experiment context manager. So any of the metrics logged to Comet under this context manager will automatically get the appropriate prefix appended to them. So in this case, the metrics logged under the with experiment.train context manager will get a train prefix appended to them. And experiments logged under the validate context manager will get the word validate prefix to them. Finally, we save our model to this asset path that we've defined up here, which is one level above our training script. And then finally, as we defined in our experiment requirements in our README, we're going to be logging the model using experiment.log model so that we can use it across our workspace, because now we can add it to our model registry. So let's go start up and run the script. So the first thing we're going to do is artifact name is HN dataset. Our target name is score. Our strategy is mean. Our message is train baseline regression model. I don't think I've missed anything. Let me just double check. Strategy, target name, and we're not using quantile strategy, so this is fine. So let's fit a baseline model using the dummy regressor, using the mean strategy. As you can see, it's downloading the artifact. If an artifact has already been downloaded based on the override strategy that you have configured in experiment.getArtifact, the appropriate action will be executed. Next, let's go with the quantile strategy. And let's specify and use the lower quantile. So right now we're just computing the first quantile on our target data set and then predicting that value for every data point in the data set. All right, now let's try using the second quantile, or the 50th percentile. And then finally, we'll use our third quantile for the 75th percentile. All right, awesome. So we have trained 4 baseline models using different strategies for the dummy regressor. Let's go to our project page and analyze some of the results from this model. So we'll go in to our project page. So we have our experiments grouped by the message, because that's the default view on this project. Let's create a new view for our regression experiment. So first, what we're going to do is we're going to go to an empty view. And as you can see, all data that was logged to the experiments are now present in the view, as well as you can see all the experiments in the project. So this is the profiling experiment we logged earlier. So now let's add a filter. So tag is train and evaluate. So that's filtered out all the experiments with this tag. And now let's do a group by message. So now we've grouped all our train and evaluate experiments by the message. So if we were to update this message or try it for a different type of run, let's say I want to train a random forest model, I would be able to separate my experiments based on these messages, but still know that every experiment in this view is a training and evaluation run. So let's also edit the columns in this view. So we don't really need the file name. We don't need the experiment duration. We can leave the username out of this. We don't need the constant value. We don't need to know the target name. Let's add some of the metrics back in. So validation MAPE, validation root mean squared, explain variance score. Is there anything else? I think that's everything we might need. So let's add those metrics in. Oh, we don't need to display the artifact name. We already know what artifact we're using. So let's do that. Okay, great. So we have, and now we can organize let's move this column here. So the variance scores are together, and then the MAPE and the train and the validation root mean squared error are together. Okay, great. So we'll save the view. Let's call this baseline regression. We'll save it, and now we'll go back to our table again. So if we want to toggle between, let's say, our messages view, and then go back to our baseline regression view, it's very easy when you save views in the UI. So let's take a look now at the metrics from our baseline regression model. So we've employed a few strategies here. We've used a quantile regression strategy for the dummy regressor for 3 of these experiments and the mean-based strategy for 1 of them. So the first thing we're going to look at is the root mean squared error. So the validation root mean squared error seems to be very comparable for all of these baseline models, for all of these baseline models. And I think the reason is that for a majority of the models, a lot of the variation, for this target, the majority of the variance in this target is in the long tail. And I think that all the quantile-based strategies and then the mean-based strategy are computing a very small constant value. So they're predicting a very small constant, which doesn't really capture much of the variance in this target. And so the effect of, if you think about mean squared error, the effect of outliers is amplified, right? So a few outlier points can really skew and blow up the mean squared error. And I think in this case, the root mean squared error is actually a measure, since we're only predicting a constant value, and this constant value is relatively closer to 1 than anything else, because that is the most common value in this target. The root mean squared error in this case is going to be the same as, I believe, the standard deviation of the data set. The next metric we're going to look at is the validation. Here we see that the MAPE values, the mean absolute percentage error, is very different across the different strategies, even though the root mean squared error for these different models is more or less the same. And so why is that? So the mean absolute percentage error is a relative measure of error. Essentially, with the quantile-based strategies, what is happening here is that for the 25th, for the first quantile, right, or the 25th percentile, I believe that value is 1 for this data set, the target, and about 40% of the target values in our data set are 1. So for all those values, the percentage error will be 0% because it predicts it perfectly. And then for the outliers, I believe, because there are so few outliers and you're only computing the relative error, there will be like a few error percentages that are about like off by 1. So if the constant value being predicted is 1, the maximum value predicted, the maximum number of upvotes in the score target in our data set is like 4,000 something. The relative error for that prediction would be about like 99 point something percent. Those are sort of drowned out because they're relative. That's why you're getting a relatively low mean absolute percentage error when you use the 25th quantile. And now as the number gets further, and as you go up in these quantile values, as the number gets further and further away from 1, what is happening is that the prediction is disagreeing with the most common value inside the data set. And so that's why the relative error keeps going up. Like in this case, I think like the 75th quantile would be, we can actually look at this. If we go back to our panels and we go back to our data frame profile, to variables. Yes, let's take a look at the score value here, double details. So Q3 is 3, right? So the 75th quantile is 3. So that would mean that going back to our baseline regression view, we don't need to save anything. So here, the predicted value for our target would be 3. So that means that for about 44% of the data set, just given how the relative the mean absolute percentage error is computed, the error would be 200%. So that's what's pushing this up and having this error metric be greater than 1. Because for about 44% of the data set, the error is going to be greater than 1. And then finally, we have these last two metrics, the explained variance score. The explained variance score is basically a bounded metric, so it's between 0 and 1. It tells you how much of the target variance is your model able to capture. Because most of the variance, again, in this target is going to be in the tail, and we're predicting a constant value that is, for the most part, closer to the head of the distribution, we're essentially capturing very, very little of the variance. What I'm guessing is for most of these cases, it's probably not 0, but like a very, very, very small number close to 0. Essentially, because you're outputting such a small constant value and only predicting in the head, none of the tail variance is explained. And so that's basically why this value is like closer to 0. So that does it for our explanation of building a set of baselines for the Hacker News performance prediction. So this is our regression baseline. So the good thing about computing these baselines is that now we have some sort of idea or some sort of bound on the sort of expected error. So if we were to use any of these metrics to evaluate, let's say, more sophisticated models, we know that just because we see maybe a low mean average percentage error, it might not necessarily mean that we have like a high performing model. It might just mean that like the model has sort of learned what the most common value in the data set is. We also have some estimates for what like the lower bound or upper bound for our root mean squared error should be. Any model any sort of more sophisticated model or approach that fails to get less than about a 68 for the root mean squared error is probably not adding much value. So from that standpoint, we have our floor, and we can build from here.